Symposium. It's a lot to live up to by Ramses Ramirez.
So I'm Ramses from Cornell University. I'll talk to you today about the habitable zones of pre-main sequence stars. I'm a research associate there. And also one of the founding members of the new Carl Sagan Institute. And I realize that this is the last talk, and I'm the only thing standing between you and dinner. So I'll try to make this short and quick but interesting. Okay, so first, before we talk about the work I've done on the pre-main sequence habitable zone, talk about work myself and colleagues have done on the main sequence habitable zone. I don't know if it's kind of, can't really see that too well. So basically, this is a plot of stellar effective temperature, with the stellar effective temperature going up on the y-axis, and the x-axis is basically the effective solar flux received by planets in the habitable zone. And it's kind of maybe blurry here, it looks like, on this. But basically you have the habitable zone is basically defined as the circular region around a star in which liquid water could be stable on a planetary surface. And so on this plot, we have these conservative boundaries, or actually these optimistic boundaries that are based on observations. It's hard to see here, but this is the use of Venus limit, and also the Mars limit here, the early Mars limit. These are based on the inferences that these planets could have had water at some point in the past. So that's how these are determined. And then we have these other limits here that are more conservative and narrow the habitable zone, based on calculations from our climate model. And so, myself and others have done these calculations using 1D radiative-convective climate models in the past few years, and actually starting off with casting, we've improved upon this modeling and come up with these what we think are more recent estimates. But most of this work on the habitable zone has been mostly done on the main sequence, as I said, and there's been some work, also on applying some of this stuff to the post-main sequence. So you can actually derive habitable zone boundaries for that as well. Although there hasn't been too much work on that. And also the pre-main sequence, this is also another area that has not been worked on very much as well. And so this is actually work that myself and Lisa Kaltenegger, and we've published the paper actually in the last year now, calculating what we think, interesting time period for a star is the pre-main sequence happens. So there's a couple of reasons why the pre-main sequence is really an interesting epoch to also search for potentially habitable worlds. And a couple of these, one of the main reasons is, well, just look at how long these pre-main sequence lifetimes are to begin with. So the red dots here just represent when the star finally achieves the main sequence. But up to that point, this represents the entire pre-main sequence lifetime of the star. And if you look basically at all these curves here, the pre-main sequence lifetimes for the M stars are pretty long. So even starting with an M1 star, you're talking about a couple 100 million years of pre-main sequence lifetime, up until about your M8 or so, which you can get over about 2 billion years of pre-main sequence lifetime. So this is a considerable time frame to really search for potentially habitable planets within the pre-main sequence habitable zone. And the other interesting observation I want you to take away from this plot is really just how much brighter for the pre-main sequence is for these later type stars, and especially the M stars. They could be 100 times or so brighter during the pre-main sequence than they are on the main sequence. And this is in sharp contrast, actually, to something like the sun. The sun, if I want to just point you here to the sun example here, the pre-main sequence luminosity for the sun is only, maybe a couple times brighter than it is today. So it's not such a big difference compared to the relative difference between the pre-main sequence and the main sequence luminosities from the M8. It's just a vastly different scale completely as to how much brighter, relatively speaking, to the main sequence, the pre-main sequences for the M stars. Now, because the sun was probably only about 2 or 3 times brighter during the pre-main sequence, if we were to plot habitable zone boundaries for the sun, it's at a certain, so maybe early on, maybe a million-year-old sun would have the outer edge of about 2.5 AU or so. And then if you were to just run this in time up until it achieves, and I should put a little red dot here to make it clear, but right here is about where the main sequence starts. Once you get over that little hump, you can see the outer edge is now 1.5 AU from 2.5 AU. So it's changed within, within a factor of 2 between the pre-main sequence. The width of the habitable zone has changed, within a factor of 2 compared to the main sequence values. Now let's look at the case for a very late M star, and the story is completely different. I mean, we can just show you how different the relative widths of the habitable zone is for the early on. The pre-main sequence habitable zone is much wider relative to the many times wider relative to the width of the habitable zone during the main sequence. And this has implications for direct observations. So if you were to, if you wanted to find planets in the habitable zone around M stars, you probably want to look very early on, when they're very young. So from very young stars, you'd see that they'd have wide, because they're so much brighter, the habitable zone would be much farther away for one, so they'd be more easily resolved from an angular resolution standpoint. Also, these habitable zones are much wider. So it's just much easier to find habitable planets, or try to find habitable planets early on in the star. The M star is very young, and much later when the habitable zone has narrowed out on the main sequence. So, for example, Apicola, which is a mid-range, mid-spectral class M star, is about 40 million years old. And you can basically calculate what the distance to it and everything. You can calculate what the angular resolution is required to resolve habitable zone planets for that star. And it's basically from about 10 or so to 25 milliarcseconds or so is the resolution. And admittedly, this is very small resolution, but it's definitely within the capabilities of next generation telescopes. Your TMTs, EMTs, GMTs, on paper should be able to resolve planets at those angular resolutions. However, there's some challenges with all of this. And one of the challenges, though, now moving on, so all up to this point, I've been really talking about potentially habitable planets in the pre-main sequence habitable zone. But if you were to take planets much further in, the main sequence habitable zone, as you know, is much closer into the star. So any planets within, the main sequence habitable zone, say your Venuses, your Earths, and Mars, or the equivalents flux planets around different stars would be much further in. They would be in the main sequence habitable zone. They would be exposed to much higher radiation levels from their star than planets further out in the more comfortable pre-main sequence habitable zone. So those types of planets would actually be exposed to high enough radiation early on to trigger runaway greenhouses near the inner edge. So myself and also others have also come with similar results on this part of the story. If you look at main sequence habitable zone planets around these early M stars, they're really vulnerable to runaway greenhouses, basically losing their atmospheres through water loss. So if you look at this line, for instance, for the runaway limits, you can see that Venus is always above that runaway threshold. So it's never in inclement conditions. Earth is mostly always above this line over all time for the pre-main sequence, and Mars is also pretty cooked for a good part of it. So this is your M8. And the story is very different from the sun. I don't show the plot here, but for the sun, Earth's pretty safe, and Mars is also safe, which agrees with why we're here. If we went runaway during the pre-main sequence, we wouldn't be here. But this is the problem with the M8 stars, trying to retain water for these late M stars that are located in the main sequence habitable zone. And on top of all of this, the other negative point, as pointed by a couple authors before, is that we predict that disk densities for M stars should be lower than, say, around the star. So it's much harder to acquire volatiles for habitable zone planets around M stars. But then, interestingly, last year, Hansen, put a pro into this, saying, okay, well, that's not really true based on the Kepler data. We think that M dwarf disk densities are actually higher than you think. So if you assume higher disk densities, you can actually acquire some water and offset some of the issues I talked about before. And there's other factors for these main sequence planets as well. You could have a late heavy bombardment that replenishes the planet just like happened on the Earth. I mean, Earth got some of its water afterwards. And so it's possible that even if M star habitable zone planet in the main sequence habitable zone gets desiccated through these high runaway greenhouse radiation thresholds and they get desiccated, they can be replenished later on through a late heavy bombardment style mechanism. And there's could have been also late state migration or gravitational scattering. Planets could scatter these planets afterwards, after the star has stellar luminosity has decreased down to a point where climate conditions can begin again in the main sequence. So I just want to leave it at that, and finally, these are my final conclusions, and I'll be more than glad to take any questions you may have. Thank you very much. And
not sure how much it matters for the temperature calculations, but can you comment on how the higher activity of premium sequence M stars affects the habitable zone boundaries?
yeah, so if we can go back to, so basically it does two major things. So when you have these, really, the thing is that your M stars, they contract a lot more slowly because they're a lot less massive than heavier stars, so their gravitational contraction timescales are much longer. And so they take a while. So they basically stay brighter relative to their final state for a longer time. And what that does is that because they take so long, then your habitable zone is much further out. They're much brighter relative to the main sequence habitable zone than for a planet like the Sun. So the Sun contracts, but not quite as much or as slowly as the M.
So I'm sorry, I was referring more to the flaring and the activity that the M stars show rather than their luminosity.
Okay, so the flaring. So that's actually a problem that's not even really unique to pre-main sequence. So I mean, certainly lots of papers will be written just on the main sequence problems with M stars in that regard. Basically, you have high enough EUV fluxes and UV flux from the star, you can basically do lots of damage to your atmosphere. And also the other thing is that M star planets, they're very close enough, they could be tidally locked, which may or may not have some negative or implications for habitability. So some people would say, okay, if you're tidally locked, it's really hard to, keep the planet habitable. You might have problems transporting the heat to the other side, but in a sufficiently dense atmosphere, I think, it's basically, thermodynamics, right? So, the hot side will, things will get transported from hot to cold. So if you have a thick enough atmosphere, I think circulations, that heat will get transported to the other side, and that should not be a problem.
So do we know what is the age distribution of M dwarfs? Like what fraction of M dwarfs, nearby M dwarfs are on the primitive sequence and what fraction is on the main sequence?
So yeah, so that's a very good question, and that's actually an ongoing work. People like after this paper got published, there are currently people that are working on target lists for pre-main sequence M stars. I think that's hard to get a handle because we don't really know a lot about stellar ages to begin with. We can get sort of there's some estimates, and very good examples that we can see better are these like close by stellar associations that are, you know, within a few parsecs away or something, or a couple, you know, tens of light years away. We can actually find these, and you know, we have some estimates of their ages, and so those would be a good place to start for trying to find, you know, planets around pre-main sequence M stars. But yeah, I wouldn't know, you know, I don't think we have a good handle, you know, the relative number of M stars are in the pre-main sequence as opposed to the main sequence. I think we need more statistics to do that.
We have time for one more.
You certainly don't want to for planet around M dwarf. There are 2 young, because planets are not there yet. It takes 50 to 100 million years to form a terrestrial planet, and it will take longer around M dwarf because of the low density.
Yeah, so that's something that's actually, that's a good point. But I mean, as I mentioned in this talk, some studies suggest that the disk densities in M-star systems are not as low as what others, you know, previous studies had suggested. So I don't know. I think that's an open question, and I mean, we don't really know. I mean, it could take longer, but as I said, like the M-star pre-main sequence lifetimes for the M8, we're talking about over 2 billion years. So that's plenty of time for planets to get formed way below that, way before that.
All right, well, let's thank our speaker one last time.